different types of background radiation that we need to be aware of. We have radon gas, we have medical, we have cosmic rays, ground and buildings, food and drink, and we have nuclear and other, if you want. Okay? Radon gas, there is a pie chart that tells you the percentages of all of them. In terms of what you should remember for the exam, always remember radon gas is the largest factor. This is in the UK as well, remember. Obviously it may be different depending on where you are. Even in the UK, not everybody in the UK would experience 49% of the radiation that they receive day to day to be from radon gas. Okay? So it depends where you are. The smallest one, 1%, is nuclear. Unless you live very close to a nuclear power station, you're probably not going to experience any radiation from that power station. Alright? So again, it completely depends on where you live, how often, maybe if you work there as well, it'd be different for different people. And then the others, obviously, as a percentage, are around 10, 11, 12%. Have a look at the pie chart in the book if you want to remember those values. Just have a think about where they come from. So radon gas actually comes from the uranium that is in some rock. Now, back in the day in the UK, they built a large area of houses with rock that contained that uranium, and that uranium just continuously produced radon. If you inhale, so if you breathe in that radon gas, then you are basically contaminating yourself, and over a period of, let's say, I don't know, 40, 50 years, all the people that lived in those houses eventually developed some sort of cancer, and the radiation obviously poisoned them and caused those mutations in their cells. Medical radiation depends on how often do you go to the hospital. Do you work in a hospital? Do you get x-rays all the time? Yeah? If you've never been, you may never experience the radiation from a hospital. Cosmic rays, they're rays from the charged particles basically, and high energy rays from the sun. Okay? Inevitably, some of those will get through our atmosphere, and inevitably some of those will be absorbed by different people in different places. If you, for example, go on holiday, you fly a lot, if you work, for example, for airlines, you're a pilot, you are going to experience more radiation from cosmic rays for someone who never goes on holiday, for example. Ground and buildings is similar sort of thing to the radon gas. In the ground, you have naturally occurring radioactive elements. They are going to emit ionizing radiation. You may absorb some of that through your lifetime. Food and drink, based on the fact that obviously most of the water you get has come from a stream or river from rocky mountains and things like that, it's going to pick up traces. But the size that you get in terms of the radiation from food and drink is going to be quite insignificant, very small. Alright? And then again, nuclear and other is your power stations, which is quite rare. It's the smallest one. Okay? There are two ways that you can actually detect radiation. Okay? Ionizing radiation from radioactive sources. Number one, GM tube. Okay? Geiger Müller tube. If you remember just GM tube, that's not a problem. Just write in your exam GM tube. And the other one is photographic film. Okay? First one, which is most simple, is the photographic film. Basically, if this film absorbs ionizing radiation, then it turns dark, turns black, if you get it processed. Okay? What this tells you is, for example, if they made it into a badge called a dosimeter, alright? If you work in a place that you know probably has a lot more radiation than any other job, you want to know every single day, your workers, when they leave, how much radiation have they absorbed. So photographic film can be made into a badge. When you leave from work that day or that week, you can have your photographic film developed, for example, and you can see, right, look at the amount of black that I have on my dosimeter, my photographic film. This is how much radiation I absorb. It doesn't give you a numerical value. Alright? I could compare it to someone else who works there and say, have I absorbed more than you have this week? And I don't even know if I showed you a card that had black on it, is that bad? Yeah, is that life-threatening or is it not a lot? It's very useful for knowing that you have absorbed radiation, but it's not necessarily useful for saying how much and is that a bad amount. Okay? Obviously over time they've developed it so it can give you a value, but as it is, just photographic film doesn't really tell you much other than you are absorbing ionizing radiation. Okay? The GM tube, on the other hand, it's made of a neutral gas inside the tube. Okay? Once the ionizing radiation enters the tube, it can ionize that gas. Okay? That means an electron, a single electron from before is broken away from an atom, so electron is produced. This is then attracted to a conducting wire, so the wire conducts current. Every time ionizing radiation enters the tube, the radiation will ionize the atoms in the neutral gas. It will free an electron. The electron is then attracted to a conducting wire in the center of the tube, and if an electron passes through a wire, there is a current in the wire. Every time a current is detected, the GM tube counts. Okay? It will be connected to a digital counter, so every time that a current passes through that wire, that means one of the atoms in the neutral gas is being ionized, producing an electron. If that happens, the current flows, the detector counts 1, 2, 3. And you can also have a GM tube connected to a loudspeaker, and you can actually hear click, 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 click. So in this case, you're actually having, look, in 1 minute, there are 20 counts of radiation. Okay? You can turn your value for how radioactive is a sample. You could say the radioactivity of this sample, if I test it with my GM tube, I'll put the sample in front of my GM tube, I will leave it there for 1 minute exactly, and I will look at the counter and it will say 20 counts per minute. Another common unit for how radioactive is this sample, I could leave it there for 1 minute, get 50 counts, and then divide it by 60 and say this is how many counts per second. Okay? The other thing you need to be aware of, what can we use the GM tube for, is for the background itself. So if I want to measure how radioactive is this laboratory, I would take the GM tube, I'd place it, for example, here, I'd point it that way, I'd leave it for 60 seconds, maybe 2 minutes. I would take a reading from the GM tube and say, okay, there are this many counts per minute or counts per second in the lab here. I may move it over there a little bit, or I might just move it around this area, but I would take repeat readings. Okay? I would measure the background 3 times, and then what I would do is I'd take an average of those background readings. Now the point in having the background in this room, if I want to measure the radioactivity of a specific sample in the lab, I'd take my sample, I'd put the GM tube next to it, and I count it for 1 minute, and I say, okay, this specific sample has a radioactivity of 200 counts per minute. Okay? But that has not taken into account how radioactive is my background. So I remove the sample, not even just move it out of the way, I would remove it completely, or I would place it in a lead-lined box, so I guarantee the radiation isn't leaving. Okay? And then I do the same thing with my background. I take my 3 readings, I find an average, and I subtract my background reading from that 200 counts per minute. Yeah? So your background reading has to be subtracted from the sample reading. Okay? Otherwise it's inaccurate. And that's your background radiation. Okay? Stop that one. What's he doing?